Hi, my name is Benjamin Jung, and today I'll be presenting my final project presentation for iterative methods of systems on alternate direction method of multipliers, otherwise known as ADMM. So ADMM is a modern-day numerical optimization method that's really useful for solving the large-scale structural problems that are present in modern-day scientific computing. As we know, many modern-day scientific computing problems are very large and highly structured, and are very complex in terms of the huge amount of the huge systems that they solve. Among the many examples include large-scale inverse problems, image reconstruction, machine learning, or even constraint simulation, where there's often thousands, millions, maybe even billions of unknown variables that we have to solve. Additionally, such problems also have to take into account such factors such as a data fitting term, a physical model, maybe a non-smooth regularizer, and additional other constraints that are often present. If you try to solve these problems directly, the resulting computational cost can be very high in terms of memory, runtime, or communication. Direct methods involve forming or factorizing the very large matrices that are present, and even iterative methods are very inefficient if they do not exploit the structure of the problem. This is where ADMM comes into play because the basic idea behind ADMM is to take these difficult optimization problems and split it into smaller subproblems that are easier to solve individually. These subproblems are coordinated through a constraint and a dual variable update, and thus the ADMM pattern is born, where you split the problem, alternate between updates, and enforce consistency throughout. An example of this might be an ADM's decomposing a large problem into one piece involving a smooth least squares problem, while another piece may involve applying a non-smooth operation, such as a projection onto a constraint set. And thus, by doing this, ADMM basically exploits the structure of the problem, and by splitting into subproblems, this takes advantage of parallel computing to come to a solution faster, as well as still maintaining the accuracy. This makes this algorithm very attractive for the large-scale problems that I mentioned before, but particularly distributed optimization, sparse recovery, and maybe just large-scale inverse problems. So now I will move on to the mathematical background behind the ADMM algorithm. So the main background or core concept of ADMM is variable splitting. Suppose that we have an optimization problem where the objective function has two different components. One part may have maybe not smooth and differentiable, such as maybe like a least squares data fitting term, and another part may be non-smooth, such as a L1 regularization term that promotes sparsity. If you apply the direct optimization method, a direct method would need to handle both parts simultaneously. This can prove to be very difficult because obviously the smooth part and the non-smooth part often require different numerical tools in the algorithm. Variable splitting solves this issue by introducing two variables into the algorithm. One variable can be assigned to one part of the objective, and the other variable assigned to the other part. And then we impose a constraint to make sure that these variables stay consistent as the algorithm solves the separate subproblems. For example, so instead of minimizing, let's say, f of x plus g of x directly, ADMM introduces the variable splitting by assigning maybe like a new variable called z, and writing the problem as minimizing fx plus g of x subject to the constraint that x equals z. This ensures that the split problem is equivalent to the original one, but the objective terms are now separated into different subproblems. This is the core background idea behind ADMM. Because the method alternates between updating each variable block separately, while the dual variable keeps track of the mismatch between them, this way ADMM can solve each subproblem separately while still ensuring that the solutions remain consistent. So yeah, now moving on to the problem form. So the canonical standard ADMM problem is written as minimizing f of x plus g of x, subject to the constraint ax plus bz equals c. In this form, x and z are two blocks of variables, where the functions f of x and g of z represent two parts of the objective function. In the constraint, the matrices A and B, along with the vector c, define a linear constraint that couples the two variable blocks. Among the many applications that ADMM is applied to, f of x can represent the smooth part of the problem. For example, it can represent, as stated before, a least squares data fitting term, maybe a physical model residual, or even a differentiable loss function. The function g of z represents the non-smooth terms such as sparsity regularization, maybe an indicator function for constraints, or projection onto a feasible set. The constraint, ax plus bz equals c, is the consistency condition. As mentioned before, it ensures that even though the variables have been split, they still represent the valid solution of the original problem. This obviously is the very general formalization of ADMM. It can represent anything from sparse inverse problems, consensus optimization, constrained regression, even compressed sensing, or other large-scale optimization models. And yeah, taking advantage of this form, ADMM is designed specifically to solve this kind of split constraint problem. So moving on to the equation setup. So the basic idea, I guess, the way the equations of ADMM have been derived is to start from the constraint problem, as seen in the general form before, minimizing f of x plus g of z. And for these equality constraint optimization, the standard approach is to form the Lagrangian, right? The ordinary Lagrangian introduces a dual variable y, otherwise referred to as a Lagrangian multiplier, to enforce your constraint. An ordinary Lagrangian would be like the term L of x z y equals f of x plus g of z plus y transpose y transpose of a of x plus bz minus c. The term y transpose a of x plus bz minus c penalizes any violations of constraint to the dual variable y. However, in the algorithm, an ordinary Lagrangian by itself is not always numerically robust, especially for large-scale iterative algorithms. ADMM instead uses an augmented Lagrangian, where the augmented Lagrangian adds a quadratic penalty on the constraint residual. As seen in this slide, I guess look at the augmented Lagrangian x e of y equals f of x plus g of z, plus the same form as seen before, and then you add a quadratic penalty term onto the end. Here, the residual is the constraint a of x plus bz minus c, and the term rho over 2. The rho over 2 term penalizes any violations in the constraint. Where the rho parameter, rho being greater than 0, controls how strongly constraint violations are penalized. This quadratic penalty is very important for the algorithm because it improves the numerical stability and encourages the iterates to become feasible for ADMM. The same dual variable enforces the constraint from a Lagrangian multiplier perspective, while the quadratic penalty gives additional numerical control over the residual. So ADMM is built from this augmented Lagrangian, but instead of minimizing this augmented Lagrangian jointly over all variables, it minimizes it in alternating steps. So continuing on with the derivation, coming from the augmented Lagrangian, the derivation of ADMM comes from applying this alternating minimization technique to the augmented Lagrangian. The augmented Lagrangian depends on three quantities, x, z, and y. While a direct augmented Lagrangian can minimize x and z together and update y, that joint minimization technique can still prove to be very expensive for the large-scale computational problems. ADMM avoids the structure by splitting the minimization into two separate steps. So the first step is the x update, where as you see in this unscaled iteration, x of k plus 1 equals the minimization of the augmentation of LP, x z to the k, y to the k. Where in this step, z and y may be held fixed at their current values. We only minimize in respect to x, and this mainly solves the function f of x along with the quadratic penalty term. The second step is the z of update, where after we have done the x update, we keep that newest value of x, but still keep the dual variable fixed. And by solving this subproblem, we involve g of z along with the quadratic penalty term again, and update z. The last step is the dual update, where we now have the new updated values of x and z, but we now adjust the dual variable in the direction of the constraint residual. If the constraint residual is violated, as the rho term dictates, then the dual variable changes to penalize that violation in the next iteration. And thus, the ADMM has three repeated steps: update x, update z, and update the dual variable. The important point to notice is that the method replaces one difficult joint optimization problem with the two smaller subproblems, plus a multiplier update. And yeah, that's where I guess the term alternating direction method of multipliers is born. The alternate x and z updates and the multipliers involving referring to the Lagrangian multiplier or the dual variable update. So moving on to a deeper look into the update equations, where we look at the scaled form and interpretation of each term. So in practice, ADMM is often written in scaled form, where we define the scaled dual variable as u equals y over rho, where using this variable simplifies the equations and makes the algorithm much easier to implement. You can see the scaled. You can see the scaled ADMM updates here, where the x update equation reduces the f of x part of the objective while also keeping the constraint residual small. Same for the z update. If g is like a non-smooth but has a similar proximal operator, this step can often be very efficient in the scaled version. And lastly, the scaled dual update equation, where you add the current constraint residual to the scaled dual variable. This interpretation is very straightforward. As before, the x step improves the part of the solution associated with f, z step improves the part associated with g, and the u step remembers any disagreement between the two blocks and pushes further iterations to feasibility. The reason why we use the scaled form is it's simpler to implement in code and analysis, and oftentimes can prove more efficient in terms of, I guess, reducing how much code you have to write. So how do we come to a stop for ADMM? When do we converge? So in many practical implementations, ADMM is monitored using two residuals, the primal residual and the dual residual. So the primal residual basically measures how well the constraint is being satisfied. For the standard ADMM form, the primal residual would be the form of r of k equals a x of k plus b z of k minus c. If r to the k is close to 0, the constraint is nearly satisfied. So the primal residual tells us whether the split variables are consistent with constraint at the end of iteration. The dual residual measures how much the dual feasibility condition is changing. So in the common form, the dual residual is x to the k equals rho a transpose b of z to the k minus z to the k minus 1. This residual basically measures whether the algorithm is still making significant changes between iterations. So a good convergence factor checks both residuals. It is not beyond looking at just only the objective value, because sometimes the objective value can appear stable even when the constraint is not satisfied. You have to have both residuals checked. So the penalty parameter rho has a major effect on the behavior of these residuals. If rho is too small, the method might not enforce the constraint strongly enough, and so the primal residual may decrease slowly. Or if rho is too large, the method may overemphasize feasibility and make very slow progress on the objective. So because of this, many practical ADMM implementations use what's called adaptive rho tuning. The basic idea is to adjust rho during the iteration so that the primal and dual residuals remain balanced. For particularly convex problems, ADMM has very strong convergence guarantees under the standard assumptions. However, if you require very high accuracy, convergence can still be slow. Because of this, many ADMM is also considered the most attractive when you place the factors of accuracy, scalability, and modularity over very high precision. So taking a look at how ADMM is connected to the broader family of methods, ADMM is not just an individual out there method. It's connected to the broader family known as operator splitting methods. This connection is important because it shows that ADMM is not just a single algorithm, but it's part of a larger framework. Some of the related factors that you can see, some of the influences of the family that you can see in ADMM is first Douglas-Radford splitting. Douglas-Radford splitting is an operator splitting method that's used to find the zeros of sums of monotone operators. ADMM is basically can be interpreted as applying Douglas-Radford splitting to the dual problem of the original constraint optimization problem. Another idea that ADMM takes in is the proximal point method. Proximal methods solve optimization problems by repeatedly minimizing a local regularized version of the objective. ADMM can also be interpreted as using proximal style updates on the split variables that it uses. Lastly, ADMM is also very strongly connected to the split-Bregman method. The split-Bregman method is became very popular for L1 regularized problems, especially in image processing or compressed sensing. The key idea behind it is that instead of simply penalizing constraint violation once, Bregman iterations repeatedly update the correction term that accounts for previous error. As you can see, this is very similar in spirit to the ADMM dual update term, where the variable y or u accumulates the constraint residual over time. So in this case, split Bregman iterations are nearly the near equivalent of ADMM applied to a split constraint formulation. And thus, ADMM, as you can see, is a mix of these different family of methods, as known as operator splitting methods, and separates the hard problem into simpler operator updates, where dual or Bregman variable coordinates, dual or Bregman variables coordinate consistency between these two updates. So let's move on to a standard example of ADMM. So a standard example is the lasso problem. Lasso stands for least absolute shrinkage and selection operator, and it's most commonly used in the sparse regression and inverse problems. So the basic form of the lasso model is seen to the left, along with the split form, where basically it involves a least squares data fitting term that tries to make the model prediction m of x close to the observed data b. The second term, lambda, is an L1 regularization term that promotes sparsity in X, meaning that it encourages many components of X to become 0. The difficulty of this problem is that the least squares term is smooth, but the L1 norm is non-smooth. ADMM can approach this by introducing a split variable z, giving the term minimization of x of z 1/2 of m of x minus b plus lambda z 1, subject to the constraint of x minus z equals 0. Now, the least squares term depends on x, while the sparsity term depends on z, and you have a linking constraint x equals z. And so you have now split the lasso problem into two separate subproblems. The x update becomes a structured linear algebra problem. The z update may become a soft thresholding, which is very cheap and applied component by component compared to trying to solve the entire problem at once. And thus, you have basically separated the linear algebra term from the sparsity enforcement, which demonstrates the efficiency of ADMM. So I just want to reiterate the many common applications of ADMM. In image processing, ADMM is known to be used for denoising, deblurring, image reconstruction, and total variable regularization. Because these problems often involve combining a data fidelity term with non-smooth regularizers. In sparse recovery and compressed sensing, ADMM can recover the sparse signals from limited measurements, lasso being an example of that. In machine learning, ADMM is very useful for regularized regression, maybe distributed training, and consensus optimization, where if you have data distributed across multiple agents, ADMM can separate these data distributions to local subproblems while coordinating through the shared variables. Inverse problems, ADMM is useful for physical models combined with constraints and regularization. In matrix problems, ADMM can involve matrix completion, low rank recovery, and robust principal component analysis, where you can apply it to split the low rank and sparse components. I guess among all these problems, the common theme is that ADMM works best when when the original problem has separable structure. If the problem can be divided into pieces that are easy to solve separately, ADMM can provide a flexible framework for reducing computational cost while maintaining efficiency. So briefly addressing the strengths and limitations of ADMM. I think we've gone over the strengths a lot, but just reiterating, ADMM is modular. Each update you can use a different solver that is appropriate for that specific subproblem. For example, one can use a linear solver, while another uses a proximal operator. Secondly, ADMM is easy to parallelize or distribute. Because for large-scale subproblems where data and variables are spread across multiple machines, ADMM can make this very easy for parallel computing to take advantage of. Third, ADMM handles non-smooth regularization very naturally. This is very important in sparse optimization or total variation problems, where non-smooth regularization can addressed with iterative methods or direct methods can become out of scale very fast. Lastly, the algorithm can be considered to be conceptually simple. The simple structure of a repeated X update followed by a Z update and a dual update it's very logical and easy to implement within code structures. However, there's very clear limitations to ADMM. One large limitation is that convergence can be very slow when you need a high degree of accuracy for this problem. ADMM can be useful for reaching a useful approximate solution for many problems, but it's not the fastest method in terms of computational speed for requiring extremely precise solutions. Another limitation is the penalty parameter rho. This penalty parameter has a very high sensitivity, and if you choose your rho, if you have a poor choice of rho, this can lead to very slow convergence or imbalance between the primal and dual residuals. Additionally, even though ADMM splits the problem, many subproblems can still require expensive linear solves, and in these large-scale applications, the cost of the X update for the linear solves can still dominate the runtime. Lastly, I guess the general limitation is that a stronger convergence theory applies to convex problems, right? And if ADMM is used in non-convex convex settings, it'll still work, but these cases may still require more caution and often more problem dependent. So it's not a universally optimal solver for every problem. To conclude, ADMM is a powerful method for structured optimization in modern day scientific computing. Just to reiterate, the central idea of behind ADMM is to combine variable splitting, the augmented Lagrangian term, as well as alternating minimization to separate a larger subproblem into separate variable blocks that can be handled by different numerical tools. The unique augmented Lagrangian term provides both dual reinforcement of the constraint as well as constructor penalty on constraint violation, leading to a very simple algorithm consisting of an X update, Z update, and a dual variable update. ADMM, as shown, is connected to and takes advantage of Bregman iterations, Douglas-Rackford splitting, as well as proximal methods to place it within the larger, broader frameworks of operator splitting algorithms. The main takeaway that you should take away from this presentation is that ADMM is valuable because it balances mathematical structure with computational practicality, and while it does have very clear limitations, and it's not always the fastest method for every problem, it's still a highly flexible, scalable, and effective algorithm for solving large-scale scientific computing applications in contrast to direct or maybe iterative methods. So yeah, thank you for listening, and see you again next time. And lastly, here are my references.